Welcome everyone. I'm Kunal. I'll be your host today for this event. If people are watching us online, hi to you all. And we are in Prague, in the KK, the Research and Innovation Center for Advanced Industrial Production. And it's a pleasure to be here today as a part of the RAASCEMAN project, which is sponsored by, funded by the European Commission. And today we'll be talking about different perspectives for digital twins and digital passports. So the workshop will start with the talk from our colleagues from RPTU, Patrick. And the first talk will be about capabilities, skills, and service models for enabling manufacturing as a service. Then the next talk will be from online via Sam and Bart from Flanders Make and ÅSKA. And it will be about a value-added DPP for e-bikes. The last talk will be given from our colleagues here from Cuba, from Continental, and from Prague University. And this will be about digital twins in smart manufacturing from theory to implementation in automotive industries. And then we will have a panel session where you can ask your questions, and we will ask some questions to the panels, interesting topics about digital twins and how it works. So just to let you know, this consortium is, as you can see on your side, it's from DFKI, from Germany, Flanders Make from Belgium, LMS from Patras, CEA from France, where I belong to, the Czech Republic, the Czech Institute of Informatics, Robotics and Cybernetics, the CTU, RPTU from Germany also, Net Company Intrasoft from Luxembourg, Continental Prague, and ÅSKA Bikes from Belgium too, and sponsored by EDI at CTU and the National Center for Industry 4.0. So now I call up Patrick from RPTU to give his talk. Thank you. Please.
Perfect. Then let us start with the presentation about the capability, skill, and service model that is an enabler for manufacturing as a service. For the first, I want to start with the current situation, how you get a product in a common way in small enterprises. And the idea is you have an idea in your mind, you're starting to modeling a cut. After that, you produce technical drawings and ask your known customers if they are possible to supply. There's something with the presentation. Then, and you contact your possible suppliers that you are knowing often. Then you get an exchange with the suppliers if there is the idea of the product and a cut is possible to produce for him or not, and that takes often time. After that, you have getting an offer. Then after the offer, you decide on your side if it's good or not. When it's not good, you are going back to the cut file and take the idea or the information from the supplier to your cut file and redesign it every time. Or you accept the offer and let the product will be produced for you. So then now I come to the theoretical part of manufacturing as a service. Manufacturing as a service is a digital marketplace for manufacturing capacity that enables the free capacity of your factory to share them with everyone on the earth. It's a global connectivity, and when the capacity is free that you can use, then it's also on-demand production. The advantages for this is the cost-saving part. Then when you are producing every time, then you are producing money in that case. Then also the speed is there because free capacity is used. And you have also scalability to different suppliers to produce the same part on the same time. And also a sustainability because there's no downtime where the machine is running. After that, I will show you the requirements for such a manufacturing as a service. That starts with the lowest point. That's the Industry 4.0 component. That is defined in the DIN spec 1345. And it says that there is a digital representation and an asset together brings you to a I4.0 component. This I4.0 component has the possibility to share your information to the network and can help you to find the best capability for your product. And the most common thing, and in our opinion of the RPTU, is the AAS for the digital representation about your product or machine in that case. And yeah, and how you can scale this up, because you are describing here a machine tool, but a machine tool or milling machine is just one part of it. You have also tools for it, and also tools can be represented in the I 4.0 component, and also robots, errors, AGVs, and also a drilling machine. And these I 4.0 components can be also known as cyber-physical systems, and each of them, I showed here, is also a cyber-physical system in most cases, but when you are clustering it to a module, then you have more parts of it together to a production module to get a more functionality of the product or of the cyber-physical system. And each, when you have many of them in your factory, then you can be flexible in every case because you have just an input and output for the production. So, and how looks the communication inside a factory, inside a CPPS? That looks like that you have cyber-physical production modules with the AAS that I shown before, and also the asset, the real asset. The real asset has skills in our cases. That is a little short foreshadowing for the CSS model that I will explain later on. And the skills for a drilling machine is to drill, and he needs an interface. In our case, a common thing is OPC-UA, and that's with this OPC-UA interface, you're getting the operating data that you can measure or monitor from the machine directly to a database or MES system, how you want it. And you have also a direct connect to an AAS share, where you can also collect the lifecycle data of the machine. And these known data will be communicated proactive between all production modules inside the factory, and will help you to produce it afterwards. And you have also, for the example, for a milling machine with the skills for milling, as also there the OPC interface and the lifecycle data. And with this together, you are possible to run a manufacturer as a service platform. And then I come to the theoretical part of the CSS model, the definition of a service, a capability and a service skill. The service is a high-level description. It includes commercial aspects like costs, carbon footprint, duration, and so on, and has links to different capabilities. Okay, and what is capability? A capability is a description that is independent of a resource. The resource is abstract of a function and has also links to the skills. And the skill is an implementation specific for a resource that you saw before. The milling machine has the milling skills. Yeah, I will run. Yes, and for the idea to show it in the first case, you see that the service is known as the milling service. Then the capability has different abstractions, like a round hole and a rectangular hole that you see here also in the picture. And the skill is often depending on the resource. That is here from the resource, the step one pocket and the rectangular pocket. That as a skill, and these are matched later on. And that matching depends on the CSS model. That is a very abstractive way that you see here. You see that the yellow boxes are for the PPPR, the product process resource. That is a very common research area before in the different papers was also discussed. And you see that there's a relation to the product, to the service, the process to the capabilities, and the resource to the skill. And the skill is very, yeah, it could be one skill for one resource. The capability has a difference with also the service, that you have required services and capabilities that comes from the product side, and also the offered capabilities from the machine side. And then you must match them for to getting an offer for the production later on. So, and you see, we are looking at the manufacturer as a service at the capability level, because the abstraction is that low enough that you can know the capability good when you are matching it, and also it's not that high enough from the high level description that you are not knowing exactly what you are doing at this point. Yes, and we are having a production example in our RPTU. That is a product for this that we have. That wasn't great. And yeah, there's this truck that is divided in some parts. You see the cabin, the front chassis, the back chassis, and also the trailer. The trailer you see has different options, one 3D printed and one milled. And you see also here abstraction of the AAS model for this milled trailer. There you see the step one pocket skills that are described in the capability description. And our shared production includes different production islands that are connected via the Gaia X data space. Inside the production islands we have an AI service, assembly service, a film milling service, and a 3D printing service that looks like this. In that shared production, the product finds his own way through the production. That's depending, or that is possible because we have also included a multi-agent system inside, that the product has an own agent that asks every production island or module if it's possible to produce me, and after this he produced me. And what you are taking with you after this presentation is that the CSS model is an forced interoperability, needs the forced also the standard description, enables also the automated orchestration for the product, as has the possibility to do the dynamic production networks, and also the modularity and reusability of the production. Yes, and that's all from my side.
Thank you very much, Patrick, for your talk, and it was very nice and interesting talk. Thank you. So I'll let you go down for now, and then in the panel I'll call you back. Yep. Am I audible? Hello? Yeah. Okay. Cool. Yeah. Better. So now we will call Bart and Sam, who are joining us online, as they could not make it here to Prague.
also see me, but that's not so essential for the presentation. Thank you for the nice introduction. Thank you all for attending here. And what we will talk about is from an industry perspective, from the perspective of ÅSKA Bikes, what value a digital product passport can bring. This is also related to the topic of today of the digital twins. We will go a little bit deeper into that during the presentation. Yeah, I have some introductory slides about Flanders Make. We are an RTO of about 1,000 researchers in the Flanders area, and we are dealing with research challenges in the manufacturing industry or in industries with manufacturing challenges on production systems, on vehicles and on machines. But this is a small introduction. Let's now go into the content of the slides, and I would like to introduce then Sam from ÅSKA Bikes, who is a production manager, to introduce the product and the challenges of ÅSKA.
Yes, hello. Everybody can hear me?
Yes.
Okay, perfect. I will start, like Bart said, I'm Sam from ÅSKA Bike, and I'm the production manager. What we do at ÅSKA Bike, we make speed pedelecs. Speed pedelecs are bikes that are made to drive 45 an hour, and mainly in Belgium, it's very popular as a mobility solution. What we do that is different on the traditional bike market is we source our supply chain almost all in Europe, while the traditional market is like 90% in Asia. Some parts we just buy off the shelf, and then the essential parts we have no own production, but we have partners that produce them for us. We do the design, and then we have production partners. There we have the battery that is essential for us, the frame, and also the assembly we do in Belgium. And I will now come back in the next slides to the different components, and also to see there the benefits of the digital product passport that we will introduce here in this presentation for ÅSKA Bike, and where we also see that we can introduce this in the assembly and the manufacturing of our bikes. So you can put the next slide, Bart. So there, the first part is our frame that we make now with 2 different suppliers. There for us, we do the design. We will make, we will have the cut of this part, and also we will provide to our partners the digital process for the production, and also for the tooling. So in this way, by have this central in the digital product passport, we can easily share it with our partners. The same for the assembly. There we have now only the instructions on paper, but the idea will there to have also virtual instructions for our workers. Because at the moment, we do this in Belgium in social economy. So this means these are less skilled people, and their clear instructions are very important for us. And also by means of a digital product, we can put this to our assembly partner. As we made a bike that goes 45 an hour, we have to homologate the bike. It's like a vehicle. It also needs a matricle. And there, very important is to have a traceability of all our components that are used in the assembly. Also, which partners made our frames, which partners made our bikes and did our assembly. This we can also have all gathered digital by different partners, but on the same platform of the digital product passport. And then, of course, the next step is that the people enjoy the bike. So it's the riding. As I said, this is a mobility solution. So people needs a bike that is always riding and that has no standstill. So that very important is to have predictive maintenance. This we can also do by gathering data of the use of the bike, not only the kilometers, but that we can really see this bike was used almost always in bad weather, or this is a bike only we use it only in good weather. It will also have an impact on which maintenance the bike needs. For example, the brakes will last less if it's used in very bad conditions. And then also using the digital product passport, we will have the instructions for the maintenance guys that is directly available what you have to do on a bike. So there we have different things we will use in the digital product passport, and also here we have the link with the mass network. I think as we have no own manufacturing facility, we need a lot of information from our partners, and our partners need information from us, how to build, and we need the traceability. And that's why this can be very important for us to have this, to exchange information with our partners. I think this was just one click more, yeah. Then another component that is very important for us is the battery, because we made them also with a partner. We did the design. A partner in Belgium is making them, because for us it's very important that this battery we can take out of the bike, and we can also repair if necessary, because after different cycles we will need to change the battery cells. It's the next Bart. So this is very important, that it's repairable. And then if you see to the next, also for us retrofitting is important, as we see that this market is changing very fast. We started with 1,000 watt, that was the standard capability at that moment, and now we see bikes are going to 2,500 watt capacity. And that's also why for us it's important that we can retrofit our bikes, and that's what we are doing at the moment. Bikes are coming in to have an upgrade to a 2,000 watt battery. And this also, if we have a digital product passport, we can see, this is this generation bike, we need to do this or that to do the retrofit. If we look for us, the most important for this digital twin or product passport, like we said, are two levels. One is for sharing information with our supplier. So as said, we work with small orders on demand, and we have no in-house production. So we need to find easily new suppliers, and these suppliers also need to be flexible, as we are also in a market that's seasonal. And so there we can use this platform to have to share all the information with them, and to get the information we need to homologate our bikes. And another level is during the life of the bicycle, we need this information of the use of the bike to do efficient maintenance. And this will also allow us to have other business models, like a bike as a service. And there it's really important that this bike is always running. And I think Bart will now explain more the technical side of this digital product passport.
Yeah, thank you, Sam. That should give everybody the necessary background to understand what drives ÅSKA and what the requirements are for such a digital product passport. And what we see is actually that the goals of ÅSKA, or the challenges, are related to sharing data across the life cycle of a digital product passport, here from design to component manufacturing, assembly, use, and also re-X. And in particular, what we see is that they are collecting and sharing design data such as LCA, but also the manufacturing process, disassembly instructions. There is supplier data needed about capabilities, about the provenance, the traceability, and quality, and there's quality assurance issues here. And then for assembly, there is a need for quality assurance and homologation. We need to be able to track the as-built information for each bike, and we need to have a certification, and we can have also certain claims if necessary. This has not popped up yet for ÅSKA, I think. Then for the use phase, we see that we are producing downstream data like service record, the as maintained state with replaced components and the state of health of each of the bikes. And then for REAX, after the end of life or the end of a usage cycle of these bikes, there's a possibility for upgrading and remanufacturing, for example, the range extender or the battery, or looking at the battery composition and state it to see whether the battery needs to be remanufactured. And what you see is in order to enable this, there's a need for data sharing across this entire life cycle. Because, for example, as Sam said, during servicing, there's a need to understand well what the disassembly instructions are, for instance, of this bike. And that is a perfect fit for using a digital product passport where all this data can be shared across the life cycle between different partners. This between different partners is a very important point. So it's an ecosystem idea. It's not like a digital twin that is used within the same company, but the emphasis is here sharing across an ecosystem. Then finally, here we see the an improved step as well, where we can couple back all the data back to the design. That's a very important part as well here, that ÅSKA Bikes, for instance, can use all this information to understand well how fast components degrade and whether they should switch to different components. So that's an improved cycle back to design that is only possible when you track the data across the entire life cycle. So, okay, let's take a step back. Where does this idea come from a digital product passport? It is basically something that has been proposed by the EU and it's being enforced through legislation. So there's some regulations that make it mandatory to create a DPP and that will make it specific what must be on the DPP. The goal is to improve sustainability and circularity of products. So that's the goal, but it's not made explicit by the EU how this should be done. So this is something for us to figure out. The point also of the DPP is that we can scan on the product, we can scan a data carrier like a QR code or an RFID, and then we arrive at this digital product passport. So it's basically a part of it is public or shared information. That's an important point, and it's a very explicit characteristic that allows us to use this data throughout the life cycle with multiple partners involved. And a very important point is also that it's that it is an identifier per product item. So each individual bike will have their own passport. That allows us to track the usage data for one particular bike or the maintenance data, service records for one particular bike. Okay, good. And basically you can divide such a digital product passport in a structure that is about model level data, batch level data, and item level data. Model level data could be, for example, disassembly instructions. It's valid for any type of this bike. Then there's batch level data, for example, the recycled content of a battery pack. And then there's item level data like the mileage. Some of these are mandatory by law. Some of these I just added because they are interested for our business case. And you can see here at the bottom, there's several potential users here involved for this digital product passport. Sam was mentioning also that they want to present a good experience to the product user. This maybe includes tracking how their bike is used as well. Also, maintainer, we have mentioned it, but there are several other potentially interested parties in the data who each will have their own view on this data. So the legislation body must be able to see whether all the provided data has been, or all the data has been provided that must be provided. That's one view. Maybe another legislation body wants to check whether the homologation is okay. That's another view. The leasing partner needs to be able to understand maybe the overall state of health of the bike, etc. So the digital product passport must be able to present several views on these data. We can generalize what we have seen earlier, as you can see here, that it's always about tracking data throughout the life cycle of a product. Now, what is very important per product and per value chain, a DPP will look completely different. It will depend on what is useful for that for that value chain or for that product. For the bikes, for example, maintenance is very important, and tracking the supply chain is very important. Okay. For example, a battery, then the tracking the state and the composition, material composition will be very important. So it's a little bit different. Now, for some products, it will be able to support new business models. For other, it is important to be able to, for example, extract the recyclable content. So it's a very different story per product. The DPP is the responsibility of the brand that puts the product in the market. It's not really the manufacturer, it's actually the brand that puts it in the market. It could be a different partner, but in the case of ÅSKA, it's the same. And then we can share the data across all of these phases. Now, in the past, there was a big emphasis on design data, for example, LCA, recyclability, etc. And then there was also a big focus on upstream data, for example, provenance of materials, energy use, recycled content, etc. And then the goal was to collect these data and to report on this. For example, you could say, okay, we can have a green label here because the total emissions are such and such. And this you could put on a digital product passport, and you can prove then to your customers that this information is correct, that you can trace back this in your supply chain, and you could have, for example, a certification. So it used to be that digital product passports were very much focused on this upstream data in order to report or make claims about your product. Now, what is also very interesting, what has a lot of potential, is the downstream data. And this is what we have been focusing a lot on with ÅSKA Bikes as well. The downstream data can help a lot with, for example, extending the lifetime of a product by servicing it well. For example, by tracking the state of health, by having the as maintained state and understanding well when to change something. So this is a bit of a shift. We come from a digital product passport that was tracking more the supply chain, and we go more to also including the downstream data. Now, well, if you create a report, it's a bit of a static. Okay. So, I'm going to take a step back first. So when we look at the downstream data, this could be an enabler for new services as well. And this is one of the things we are looking for together with ÅSKA Bikes and a number of other partners in a different project. We are looking into, for example, a new business model around bike as a service. So that's an important thing you can do. And we see that only possible if you have the downstream data. There's also some challenges with that. Before, if the goal was for the DPP to report and for example, put a label on the products, it was a fairly static document that had to be delivered when the product leaves the gate of the manufacturer. Then you can compile all the information, collect it, and provide it with your product as well. What we see now is that we require much more dynamic DPP. It's very important to have a common understanding of the data between the partners in the value chain. If we're talking about service records between two different servicers, how are we able to understand each other there? It also requires a lot of trust and openness in data exchange in this case, because suddenly different parties are adding new data to the DPP, such as service records or such as usage data, etc. So it's a very important that this is an ecosystem story, and you need to get the partners at the table here in order to develop these new services or new business models. So that's the consequence of this shift from upstream towards also more downstream data. This has had also some technological consequences, but that's a bit out of scope for today. You can ask me about it if you're interested. Now, in the case of ÅSKA, what does this I can very quickly show you what this digital product passport looks like when you scan it as a servicer. When you scan it as a servicer, you simply see the upcoming servicing tasks. Very simple information, but behind it, there's a lot of data sharing. In order to know that we need to replace the drivetrain belt on the 3rd of May, there is information needed that comes from ÅSKA bikes, that comes from the previous servicers, and that comes from the user with the usage data. Based on that information, this date is calculated. The expiration date of your drivetrain belt is calculated. So here you see this ecosystem in action, where there's data from different partners that is used on demand here in order to provide new insights for one of the partners, namely the servicer in this case. You can also then access the right documentation depending on the particular bike he has in front of him, etc. So that's a very simple, it looks very simple, but there's a lot of data exchange and agreements behind this. All right. The goal is here to come to the win-win in the value chain where data and knowledge is shared among the partners. Okay, in view of time, I will skip this slide. It explains better this win-win across the value chain between 4 different companies. So this is an example where the digital product passport shines. Now, the key takeaways maybe are threefold here. A digital product passport is not just for legislation, but can add value. This was the story that we wanted to tell you with ÅSKA bikes. It's not just about a digital twin, making a digital twin basically of the life cycle, of the full life cycle of your product. It is about setting up data ecosystems in order to get to new opportunities and new business models. It's a very important enabler for such business models. What is the connection between a digital product passport and a digital twin? Basically, a digital product passport is a carrier for digital twins to be able to share them across different partners in a value chain. So this means that you can expose your knowledge and your digital twin to the right parties as well in order to, for example, provide a degradation model of your bike or of components to a third party that does the servicing. These were the key takeaways. We will share the slides afterwards, and if you go further into these slides, that you also see 2 small movies that demonstrate this DPP in action. But for now, I would like to thank Sam for your introduction of the ÅSKA case, and I would like to thank all of you, of course, for coming, and I would like to thank Kunal for hosting us today.
Thank you, Bart. I think it's thank you, Sam. It's one of very good slides about DPP, and I think it supports our people here to understand a bit more about difference between DPP and digital twins that we have been discussing today. And really interesting key takeaway, Sam. Thank you for this. Thank you, Bart. Thank you for this. And now I call upon Jakub from Continental. He will be talking about his experiences, about the work that's happening at Continental. And yesterday we were there in their location, and I think it's a very state-of-the-art work happening. I'm very impressed by Continental stuff. So it's to you, Kuba, now.
And thank you, Kunal. And always my intention is to connect the academic field with the real manufacturing, because you are sitting on the shop floor on the test bed, you like a computer scientist sitting 100% in front of your computer and making good magic. But later on, you have to come to the shop floor and there everything is visible. And so let me introduce myself. My name is Jakub Hamerník. I am the head of the smart automation for the complete business area UX in a Continental, and me and Tomáš Jochman will present something from the digital twin in the manufacturing. How is intention in the case of the product, machines, equipment, and the processes. I can switch it off myself. But before we will start, it's not only the Continental or the CIIRC or ÅSKA Bike who is using the digital twin in a different field of the manufacturing. Red Bull Racing, Luna Rossi, Bianchi. All of these three brands using the digital twin. The first using the NX designer, creating each part in an NX, simulated, validated, produce it later on, and then share all information in the PLM system. The Luna Rossi, one of the high-tech boat, the winner of the American Cup, again, NX designer validating, evaluation, the complete boat before they produce it and they start competition. Bianchi, in the last years, they invest a lot of money to the digital twin of the process description, and they were able to increase the output from the production by the 500%. What I want to mention here, the Continental is on the good way, and I believe the academics here and all our partners too, because we are using the same software portfolio like these three very famous brands on the world. And coming back to the product lifecycle, Bart is already speaking here about the lifecycle. We have a product lifecycle, compare with the processes, compare with the task, and all is described in several milestones, which is giving you the hints what has to be fulfilled during a product introduction to the market. And it's a very nice example how we act, because based on our PLC, we call it PLC, we create the digital trees. And digital trees, this is one of my favorite picture, because now we can spend additional 5 hours to describe this picture. But honestly, it's nothing else, only the visualization of our processes, use cases, and the technology behind. This is the process itself. And if you will ask me how we can use the digital twin in the manufacturing, I can say it to you that one digital twin is already our input. And this is the description of the product. Then we are starting with the value stream mapping, how we will produce. AMR, how we will transfer the material to the production lines. We are designing the production lines. We are performing digital lean check. The VCOM. VCOM is the virtual commissioning, one of the key, and I will later on speak about it. And for sure, the change management. Because for us, it's very important that each change on the equipment will be in the future validated in a digital environment. And you never touch the production equipment which is produced before validate and release the change. In the PLC, in the robot codes, on the product itself. Then we have several use cases. I will not go through. There is a lot of use cases already using the digital twin, using the simulation tools. And one famous is that the cycle time validation, robot code validation, PLC code validation. 10 years back, it was not possible. The simulation level I skip because I think the better part of the presentation have Tomáš. But in operations, we are using the 3 types of the simulation in the machine, production line, and factory. And the 0 level, and we make it happen because we said we want to start with the 0 level, which is the product simulation. Coming back to the virtual commissioning is nothing else than the parallel activities thanks to the digital twin in the virtual environment. Thanks to the cooperation with the CIIRC, thanks to the cooperation with the Siemens and the other companies, we was able to achieve the ratio 1:1. That means our production line act 1:1 like in the digital world, and the same behavior was visible on the real world. My colleagues from the RAASCEMAN already here see this video. Ah? Now. So I will come back. Can you switch? Yeah, perfect. It's only the 10 seconds, and there is a collision with the robots and an OK conveyor. What happens? If you are a lucky guy, you will only change the grippers. If not, you are changing the complete robots or complete station. Again. And how we want to use the digital twin, especially for the process description in a RAASCEMAN project, because our use case, like automotive partner in a RAASCEMAN, we will focusing with the team for the operative production planning or reschedule the production plan based on the unforeseen event. Based on our data, based on the environment, based the sources on our supplier side, and in a complete supply chain. Here you can see the digital twin of the layout, which is connected together 18 production lines, and you can see already the AAGV is running through the shop floor. That means this simulation describing the status 2026. So we are already 1 year above or in front, and now thanks to the RAASCEMAN we are connecting this model across the OPC UA with our real asset. That means in RAASCEMAN we will have additional information coming from the production, how the production run in real time. And my last slide, and then I will invite Tomáš to this stage, because we discovered the very nice platform NVIDIA, and we are cooperating with the Czech Institute of the Informatic, Robotic and Cybernetic here for the simulation of the vision system. Because during our virtual commissioning, we discovered that we are able to evaluate the robots. We are able to evaluate the logic, but the camera, screwdrivers and everything what you can install to the shop floor was for us the black box. Thanks to the NVIDIA Omniverse, it will not be the black box, because we will be able to debug it in front, and we will be able to validate the behavior of the real camera, for example in this case, on the screwdrivers in front, and validate the complete code. And the video, and I'm already, Tomáš, you can go, this is my last video. This is the NVIDIA Omniverse, again, the complete 3D model connected to the OPC UA. We are collecting the data here each 100 millisecond, not crash the PLC, yeah? So it's not nice, but finally, theoretically, you can go to the 1 millisecond collecting the data through the OPC UA. And then you are only visualizing the NVIDIA is it's a visualization tool, like the graphic in Excel, always. And that's all from my side, so thank you for that. And now let's continue with the Omniverse, because Tomáš is the expert.
Okay, thank you, Jakub. Hello, everybody. My name is Tomáš Jochman, and I am in direct contact with Continental AG, and we are trying to, because the slide in the presentation which was skipped was also called end-to-end simulation. I think that this is your term, which you introduced into the industry, and now we are trying to make the new end of the end-to-end simulation with the NVIDIA Omniverse. So now I will show you what are the challenges, use cases, and how we dealt with them. So as you can see, the current state of the simulations is Basically, we have some rigid body simulation. We can connect PLC, HMI, AGVs, everything into one simulation. But in reality, there are also some other, I would say, tasks which were not possible to simulate yet. And why I'm saying yet is that one of the tasks is machine vision or simulating cameras. And it's necessary to have photorealistic environment where you can actually do it. So to overcome these challenges, you can see here, we focused on direct connection of the workplace, robotic workplace from Continental into NVIDIA Omniverse. So as you can see here, it's not, I would say, that good like on a PC, but you can see that this environment enables to show shadows, reflections, light sources, and all those stuff from real world, which are not possible to simulate yet directly within the production equipment. So thanks to this visualization platform, we use this solution and design our methodology, implement AI models for vision tasks. And thanks to this, we can collect the data from the simulation, train our models, and then also validate it in real production. This platform also enables rapid performance in comparison with other softwares. For example, now we are working on a project where we are running graphical calculations not on CPU but on GPUs, and we got 20 times the time for the simulation necessary. So that's rapid decrease on the computational load and everything. And as you can see, I will show you a video now where it's described in one package, and this is the workstation we focused on. It's a robot equipped with tightening system, basically screwdriver, and camera system. Why there is a camera system? Because each part has its tolerances. PCBs and all the covers are manufactured with some tolerance and transported within some destination, also with another tolerance. When you sum it up, you need to have the camera on the robot because it's really precise tasks to do the screwing. So in the left picture, you can see the photorealistic render from NVIDIA Omniverse, and on the right side, there is a real camera image. In the left, you can see that some of the actually parts of this part are seen better than in reality, but that's only based on how you actually design the textures on the model, so it can be enhanced even more. And you can train this model and then do it in reality. So in here, do we have also sound? Yeah.
Step into the metaverse with a digital twin. In a virtual environment, accelerating development and ensuring high accuracy without physical limitations. And with real-world data, refining the model, simulation and production come together, unlocking true industrial intelligence.
So as you can see, now it looks like almost all the problems are solved, but it's not that, because this was just 2D application. You know, we were trying to figure it out, the translation and rotation of the part, but we would like to go even more into depth. That's 6D post-estimation algorithms to find the part in the space, and it's a bit more tricky, but we also work in this area. And I think that in the future it could be definitely used in the production. Another short video.
6D pose estimation is a critical task for pick and place.
Sorry. Let's try it again.
6D pose estimation is a critical task for pick-and-place applications. It can now be solved in the industrial metaverse and even enhanced with AR headsets for real-time operator guidance. In the metaverse, we project the real workplace. AI algorithms detect the object in the physical world, replicate it virtually, and simulate the entire process in real time. If the operation is validated in simulation, the task can be sent directly to the real robot or executed fully autonomously. This seamless integration bridges simulation and reality, delivering safe, efficient, and intelligent automation.
So this was also really, I would say, important step to the future, but there are a lot of other processes which were also not handled yet. But we found out that within this platform, it's also possible to do multi-physics simulations. That means that you could simulate even like, for example, adding the material, the exact physics behavior of the material. And here is a showcase from a gluing station at Continental. And as you can see, it's also possible to, within the robotic system, to simulate the gluing, which is quite new and I would say really useful for the future. So that's everything from my side, and thank you for your time.
Thank you, Tomáš. Thank you, Kuba. I think it's amazing to see what technology is coming up. And I'm really happy to see the collaboration between the universities and the real shop floors that we saw. And now I will call upon all the speakers, online and physically. So Patrick, Alex, Kuba, and Tomáš, please join us for a panel session. So we have prepared some questions, but we would like the people here to ask some questions or online. I think today's session has been very informative. So again, I will quickly tell about our panelists. So we have Alex from DFKI, German AI Institute. We have Patrick from RPTU from Germany also. We have Kuba from Continental Prague, and we have Tomáš from your institute. And I'm Kunal, I'm from the CEA, the Commission of Atomic Energy for France. And we have Sam from ÅSKA Bike online, and I hope there is also Bart. I can't see him. Bart, can you hear us? Yes. Now we can see you. Okay, so I will start because let's say Alex is sitting here on the first side on the panel. So let's start with Alex because we didn't give him a chance to speak today. So please pass him the mic. So not a very complex question, Alex, simple, and whatever we can help our people online and offline. So the question that we have for you, Alex, today is, what is your take on digital twins for cyber physical systems perspective? So we have heard the DPP part, the digital twins part of different perspectives. From your perspective at DFKI, what's happening? What is in the cyber physical system, the robotics part? What do you think is the future, the current status? So if you can enlighten us.
Yeah, thank you. Thank you for having me here. So there are these two emergent concepts of, on the one hand side, cyber physical systems, and on the other side, digital twins. And although we might see here a lot of similarities, but there are also differences. For example, in cyber physical systems, we focus on very tight interconnection between physical and cyber, and more focus on autonomous behavior of the system. Though in digital twin is a digital, again, representation of some asset, and then this digital representation, let's say, may live in this digital world in simulation and so on. We might have some simulations and then transfer results back to physical. So some researchers trend to separate these kind of concepts. I would have more holistic approach here and just provide several examples how cyber-physical systems can work together with digital twins or benefit from digital twins. So first of all, digital twin might be, let's say, part of cyber-physical system. And here, digital twin must provide the single source of truth. I think Jakub also talked about this. So again, system must have true information about an asset, machine, controller. So digital twin must provide it without given some assumptions. So we need this current. So this is about synchronization. This one thing. And the other thing, when we go more into autonomous behavior of the systems, maybe to the future, autonomous cyber-physical systems will have to make some decisions when they communicate with each other. And here we need that they can answer if questions. So kind of answer what would be if I do this. And here without digital twins and of course simulation, we cannot do this. And here digital twins really can shine.
You saw the presentation from Kuba, and he was saying with NVIDIA Omniverse and with Siemens, there is a one-to-one mapping between the digital twins and the real physical system. This is what you are thinking about?
This is what I'm also thinking about, but imagine that if we have cyber-physical systems, cyber-physical production modules, robots that act autonomously, and then, I mean, I'm talking about the future, let's say. Mm-hmm. And then in parallel, we have some type of digital twin simulation, but running much more faster in parallel. Yeah. Okay. And when this cyber-physical system need to decide, this is one of the possibilities how this decision can be made, because we cannot in the production we cannot just try things. Yeah. So we cannot just. As people, we can try things. If something goes wrong, we do something else. But in production, we cannot do this. Somehow, we must have possibilities for this. And these digital twins, again, realistic digital twins that synchronize with reality, again, running much faster can provide this possibility.
So if I understand it clearly, you are thinking of the operation time digital twins, not at the design time, right?
Yes, I'm talking about operation time. I mean, this is more operation time, synchronization with cyber-physical system acting in the real world, and in parallel digital twins.
Thank you so much for your time.
Yeah, thank you.
And I give the mic now to Patrick. I'm going for a sequence because the first talk was from you. So, Patrick, I will ask you one question for now, and then depending on time, we will have more questions. And because we have to ask a lot of people questions here, and I want to give chance to the audience also. So what are the biggest challenges that companies are facing from your perspective, from the traditional models to the CSS model that you were talking about? And how can they overcome it, if you can overcome these problems in the future? What is your perspective on that?
The main perspective is that most or the small enterprises have just one supplier and are fixed in one product or PLC company, and then it's often you don't have the interoperability between different companies to exchange on a manufacturing as a service platform. And for that case, you can say, okay, there's a possibility to say, when you abstract the functionalities of each PLC or of each machine that you have, that can be from a milling machine, from DMG Mori, Hermle, what are kind of milling machine you comes in mind. There are different ideas of cycle systems or something else, and that then you have the possibility to say, okay, you can match them to one system and says, okay, if you can produce it on this machine, you can also produce it here, because you have the abstract of the capability, and to drill a hole is possible for each of them, but the expectation of is the right tool there is something different, but the capability and also the skill for the specific resource, the specific machine, is the key for it.
So if I reiterate, it's the interoperability which is very important in the future, as you were saying, right?
Yes.
So it's how the different capabilities can be matched to each other, to the resources, to the products, like a robot with a drilling machine and different robotics for different machines. Okay, thank you so
Correct.
much. Yeah, I will come back to you if we have time.
Yeah.
So now I go to our speakers online. I don't know if I'm visible to you. So maybe my first question goes to Bart. And I think, Bart, your presentation was very awesome. I liked it, the DPP. It was very clear. You gave a very good perspective about the laws, what we need, and the ecosystem. So from your perspective, what are the main lessons that you have learned till now in the DPP perspective from, let's say, the ÅSKA use case? And how and what could be done, not only for RAASCEMAN, but generally, that we can create this ecosystem in a better way? Because something that you said very interesting during your presentation was the Commission is thinking of creating this DPP ecosystem, but they are not giving how to create it, but just an idea. So what is your experience, and what can be done at the researchers, RTO level and academics level, please?
Yeah, good question. Some lessons learned that we have is the current state is like the Far West in the late 1900s now. It's chaotic, rough, lots of opportunities. There's still gold in the rivers, but the sheriff does not have a lot of power over the entire Far West. So what we see is there's a big need for standardization. There's a lot of initiatives driven by the EU in order to do that, because standardization will be key when exchanging information between different parties that may not know each other. Yeah. So that's one thing, standardization. A second thing is, and I think I mentioned it during the talk as well. What is very important, what we see is that, okay, there's going to be the standardization, there's going to be the legislation, they're going to prescribe what you need to do, but every case is different, and you need a good way to think about what value will these opportunities like a digital product passport bring. In that sense, it's the same as any technology like a digital twin or NVIDIA platform or whatever. You need to figure it out for yourself what it will bring. And it's going to be a vastly different idea for each case. So we need a good way to think about how to figure this out, what it can bring to your value chain. And for that, I think it's very important that we keep a systems thinking perspective. Systems thinking, getting all the stakeholders together, etc. So we need to break out our silos. And it's not an easy way to do. It's maybe a mind shift for several people, but I think that's a good takeaway to say that's a systems thinking, systems engineering way of approaching this, getting a business model in the mix with your technology, experimenting with this, finding a good way to incrementally experiment with this. That's going to be the key.
Okay. Okay. Thank you so much, Bart. I think makes total logic what you are saying. It's systems thinking is very important for us in the future, and I think slowly, even at the Commission level, at the European level, we are going towards breaking the silos. So I have hope, and we will see what happens. Sam, to you, it's a simple question. So from the ÅSKA side, as a industrial partner of Flanders Make, what has been your key takeaway to partner with RTOs and academics? How and what do you think will be interesting for you as a company, and some insights you want to share with us? Something generic, nothing complicated. Don't worry.
So for it, it's very interesting to make a step in our production to go to an higher level. As a small company, we started with everything on, let's say, Excel files, and now we will go to this digital twins of our production, and this will give a lot of opportunities for our quality assurance. To get easier, also the homologation, that will be very important, that we have a good traceability of all our parts with a lot less efforts than we are doing now. because now we are just exchanging with every supplier on a different platform and on a different way. So this standardization for us will help a lot to get it easier in production. But also in the project, I think to exchange with different suppliers information. This will help us, and with Flanders Make we can make this step, I think. And that's what we also see in the project with the maintenance. This equivalent kilometers and everything will help us to do a better maintenance of our bike and to have a better life cycle of our bike.
Thank you so much. I mean, and I think the use case that Bart has shown from the ÅSKA Bike makes too much sense also, especially what you said, Sam, that things are changing, the wattage of the batteries. You have to see how to have the backward compatibility, how to have the standardized systems. I mean, it's very interesting to see, and how all this data in the value chain will flow into a DPP so that we can create better systems, better ecosystem exchange. Thank you so much. I'll go next question to Kuba. I will ask you a bit more philosophical question, but no. So Kuba, you have been implementing digital twins at the Brandy's plant, and we have seen the plant. I'm very impressed. Very, very high, nice standardization and technological maturity. From your perspective, what has been the benefit of the digital twin concepts at Continental level? What was, I mean, if we don't have this right now, what would have been changed? What's your key takeaways?
So, only thank you. Thank you for a digital twin. We can be much more competitiveness with the Chinese suppliers, decreasing the lead time of our machines, lead time of our product to the market. And this is why we make it happen, because the traditional process flow is not feasible. Yeah. So only for your information, in the past we spent 2-3 years to ramp up our production lines, and now we are doing it in 1.5 year. And the digital twin have a very important information during a design phase, during a production phase for us. So the final manufacturing process is much more effective at the end.
Okay. Thank you so much.
You're welcome.
Yeah. Tomáš, to you. I mean, the videos of NVIDIA Omniverse is very interesting, and let's see what it comes up. So, to which level of details can we really simulate in the Omniverse ecosystem? What has been your experience and takeaways?
So basically, the level of the simulation is based on the, I would say, user experience, and also the ratio of like cost and time you want to spend with. Like, I think that it's critical for each application. For example, we are now trying to develop some kind of module for additive manufacturing there, where you can actually simulate the whole process. And if we would get more into the depth, it would be more complicated, and it would we would spend more time on it. So it's you need to find like a sweet spot there, and you just need to define like what is the level of the simulation you would like to achieve. And for example, if we would talk about some assembly or some let's say pick and place operations, in this area it brings a possibility to, for example, simulate I don't know, like a robot transporting some metal sheets. This is like a really easy example. In normal rigid body simulation, you would just have a plate, you know, like a stable, but in reality, you know, it will deflect like into the U shape. So you wouldn't find out that there are some collisions with the objects around. So those are like the opportunities you or user can develop and use it.
And in your experience, is it getting better and better to use? I mean, if students in the university want to use it, do you think they should start working on Omniverse, or are there any other comparable ecosystems that they can work on?
Yes, definitely there are many, I would say, other platforms. if we would just focus on the rendering, we can use Unity, Unreal Engine, Blender, and so on. But in here, the advantages are much like deeper, because they are not only focused on the rendering. This is just a tool which you can use, but it's not necessary. You can just run the computation in the background, like with headless mode. But the main advantage is that you can actually accelerate the computation within RTX graphics card or servers, and like transferring your computation from like normal, I would say, user application to the graphic card. Then this is like the main advantage, like for the future, because like in comparison, if I would run a virtual reality scene there within standard application, like the load on my PC is like 90%, and within this is like 20%. You know, because it is a lot of optimization behind, even like with the rendering and also with the calculation in the background. So
thank you so much. I have more questions, but first let's ask the people here and then online if they have some questions. So Teresa have already sent me some questions. So anyone has a question that you want to ask the panel? Be free, it's okay. Nothing political, but something normal, please, anyone? We have big experts here from different countries for you, so feel free. So I think everybody understood everything, so there is not much. Oh, we have a question here. Please, can you give a mic to? Yeah, better, because for online also it's better.
Thank you.
Can you introduce yourself also?
Hello, my name is Petr Novák. I'm a researcher at this institute, CIIRC.
Okay.
And my question is related to the information model of capabilities, skills and services, CSS. Do you have any information whether this is still rather scientific idea or theoretical approach, or is it like regularly used in industry? And if it is used, or in both cases, what are the challenges in this area? Is, for example, the scheduling or planning of the production, is it a solved task, or are there any open issues still?
Yeah, also for the first question, the production in the industry is not on a CSS model based at the moment, but we have shown our shared production. We have also shown the Recape production. There's also based on the CSS model when I have to write. Yes, and there is the approach shown in a small demonstrator, which has the transport system, has the separate modules that are working on it, that has also the OPC-UA communication to it, that has the intelligence to exchange the information, also from monitoring data to input data, and also the result data of the feasibility, if it's possible to produce it, or to use the skill or execute the skill. And to the second question, the main advantage is to implement at the first the skill and the capability to it for the industry and also for us, because at the moment we are producing the functionality separately for each module. And if this is possible to say, okay, if we... Do you want to say something? Okay. Is it so that we are, depending on our module, must implement the skill? And when this is possible to say, okay, we are just uploading one file to it, to one application, to this app-based PLCs, to say, okay, you now have you have the skill, then it's possible to explore the CSS model to the industry, because then we have the possibility to be flexible on this case.
Okay, thank you.
Yeah, I just want to add something to it. Yeah, of course, it's still the concept, and we need to raise that area of this. And also, I think the production, we need some mind shift here. So because we are speaking here about some abstract things like skills, capabilities, and so on. I think Jakub doesn't think in this kind of thing. So he thinks in terms of KPIs and so on, and then cycle times. For us, this pretty abstract concepts help us to again reach some flexibility in when we have when we need it, when we face the need to reconfigure quickly our production lines, and here this model and then the technology which will eventually come and mature will shine, but still kind of it's still in the research phase.
Yeah, thank you. I think it helps you to get the solution. Yeah. Any other questions amongst our audience here? No. So we can take a question from online. Is from Jamal Osturk. And this question is, of course, he's saying thanks for the presentations. Would you mind share your opinion if you see an opportunity to use agentic AI technologies towards cognitive digital twins? So it's an open question to anyone in the consortium, in our panel or online to Bart and Sam. The question, again, I'll repeat. It's a very interesting question because we know that agentic AI is on rise and people are using AI agents. We have projects already done on that with DFKI before. So the question again is, what's the opportunity that we see towards cognitive digital twins using agentic AI? Thank you, Teresa.
I would start a bit from other perspective. We are already using agentic AI, let's say. We're using agents. We have multi-agent systems. I know that now we have kind of rise of this agentic AI, but agents are being used in research, in academy, and partially in industry for some applications for long. Yeah, here we talking about cognitive agents, but probably they will be part of our multi-agent systems. We have other agents. Here also, I see the importance in interactions between agents, how they interact with each other, and what then added value they bring. Yeah. Here also, when we bring these cognitive agents to the industry, we must be sure that they are reliable. Yeah, that's completely other perspective. So one thing to have some agents which is chatting with the user online, and completely other thing when this agent decides again something and robot then crash. So, but again, agents are being used in. Yeah. We use them.
I think I can comment because I work on agents now too. So there has been two different interesting opportunities on agents now. It's the MCP from Anthropic. Have you heard about this? It's the protocol. And 2 weeks back, Google has released A2A, agent-to-agent communication for a multi-agentic system. So I think the opportunity is getting better and better. And the A2A, if you can go to the GitHub of A2A on Google, you can check what it means and how the A2A will talk to MCP. I think the idea is the trustability part is very important. We have to understand that machines don't talk in natural language. Machine talks in standardization. So the online, it's a different thing to discuss with ChatGPT and to have an idea, but you cannot have LLMs talking to each other through natural language and the machine cannot work. So there is some very interesting, I will not say papers, but blogs people are writing that you have to convert from a natural language to an understandable model that could be understood by a system, and then the system talks to system, and then it can talk to another LLM to give you an answer back. So, but I think the opportunities are very interesting, especially because through a natural language, you can talk to a system, and the system can be connected through MCP protocols to different other systems and can give you results back. We will see how it will work out. I'm not sure about manufacturing, but this thing is happening in digital twins in not just manufacturing, but in healthcare, in energy sector, in smart communication, smart factories, smart cities. So it's a lot of potential, I think. We will see. Any other, somebody wants to add this topic? Agentic AI? No. Online, Sam, Bart, anything about, you want to speak about agentic AI in your work?
Yeah, I'm not myself working on agentic AI, but if we look at the project that we are representing today, it's about manufacturing as a service, and manufacturing as a service, you can see it as a system of systems. And when you look at a system of systems, an agentic approach makes sense, where you have multiple agents that interact with each other, and each of the agents are autonomous. This is a good reflection of the reality. So that could be it's a reaction to the question, opportunities and towards a cognitive digital twin.
Yeah.
It makes sense, I think, to look at a manufacturing supply chain as such you can make a digital twin of your supply chain or of your supplier network and simulate your scenarios on it by using agents. These are, in my opinion, the kind of interesting and largely untapped opportunities about agents. I think it's a different look at it from what you said, Kunal, because what you say is more really the hard agentic AI, where you use different agents to solve a signal problem. Less so, I'm talking about an agent to represent a system of systems. But in that sense, I liked the remark because it sparked a little bit, for me at least, the idea of, look, there are definitely opportunities to use agents in the context that we are working.
Yeah, I totally agree with you. Thank you for this point. Any other questions online we have? Okay, thank you online for having less questions for us. Again, anything else? We still have, let's say, a minute before closing. Any other things you would like to speak before closing, especially our partners from Continental? Thank you so much. You're so kind. Okay, so I think the takeaway today here is that we have experts that you have heard from different perspectives of digital twins, digital product passport. And I think what we have heard about the passport and how it links to the twin is very interesting work, and very good question about the CSS models, and good answers that it's still a bit theory, but still happening. So we will see. And with this, I think we can close this session. And I thank you all here physically and online, and all our panelists to be here. And thank you, Sam. Thank you, Bart, for taking out time for this panel. Thank you all. And special thanks to Eva and Teresa and the team here from communications, because without you guys' support, it's not going to happen. So thank you again. And I can finish this session. Thank you.
Okay, bye.